Hello everyone, in this video I'm going to be explaining the problems to Leetcode Weekly Contest 264. So this contest I think was a relatively easy one compared to previous ones because I actually managed to solve all the problems. I did start 5 minutes late, but I did manage to finish in under an hour technically, so I'm proud of that. Okay, so problem 1. It asks us to find the number of valid words in a sentence. So they give this definition for what a valid word is and tell us to count how many valid words there are. So a valid word is given as a word that consists only of lowercase English letters, hyphens, and or punctuation, where punctuation are the 3 characters given here. Just that. And then the word can have at most 1 hyphen, and if it is a hyphen, it must be surrounded by 2 lowercase letters. And in the word, there needs to be at most 1 punctuation mark, and if it exists, it must be at the end of the word. So we split the string up by spaces because that's how words are defined, and then we count the number of the number of valid words. You can see this isn't like a very hard problem, but it's quite complicated to code. So basically what I did here was just make a function to tell if a given word is valid or not. To do that, I used regular expressions to tell if it fits this only containing lowercase letters, hyphens, and or punctuation condition. If you don't know what regular expressions are, they're very useful. They're used for matching strings to a given pattern. So if you don't know what that is, I'll put a link down to that in the description. And then I just check the hyphen condition by checking that there's at most 1 hyphen and it's surrounded by lowercase letters. And then I check the punctuation, that there's at most 1 punctuation mark in the word and it's at the end. And then, and then I just split the sentence up by spaces and counted how many words were valid. So overall, pretty straightforward problem. Took me a while to code. But yeah, this is mostly just string manipulation. Good for practicing strings. Okay, problem 2. Next greater numerically balanced number. Okay. We are told that an integer x is numerically balanced if for every digit d in the number, there are exactly d occurrences of that digit. So for example, 0 cannot appear at all because 0 needs to appear exactly 0 times, and this can't be in the number. 1 needs to appear once, 2 needs to appear twice, and so on. So I give some examples here, like 1333 is numerically balanced. And we just need to find the smallest numerically balanced number bigger than the given input. And you can see that the input is actually quite small. So it's not like 10 to the 7 or something. It's only 10 to the 6, which means that we can actually bash this out. So I use C++ because Python probably would have been too slow for this. Basically, I converted, I made a function, a method to return whether a given number is numerically balanced. And for some reason, they gave the name beautiful here. So that's what I went with. Beautiful, balanced, same thing. So this method tells if a number is beautiful or not by just going through the string, basically, counting up the number of occurrences of every digit, which is stored in here. And then at the end, the digit either needs to not be in the string at all or match its number of occurrences, which means 5 appears 5 times, for example. So yeah, this method should be pretty self-explanatory. It returns false if at any point no digit matches that condition. Otherwise, it returns true. So that's that function. And then I just incremented numbers until I got to a beautiful one. And we actually know that there's a relatively small beautiful number after 10 to the 6, which is 7777777, which won't take too long to loop to because if you know, 10 to the 8 is a reasonably small number of... what I mean is 10 to the 8 is the maximum bound for the number of operations you can do in a reasonable time limit. So the numbers are small enough so that we can actually just bash this out. I do have a complaint, which is that the first time I submitted this, it was time limit exceeded. And then the second time, the only thing I added was this hyphen greater than, which is the C++ way of calling a method within a class. And I don't know why that just made it accepted, but made me angry because it cost me 5 minutes. Okay, problem 3. count nodes with the highest score. Okay, so we're given a binary tree, and the structure is kind of weird because we're given the parents of every node, and usually you're given the children, but actually this is it turns out that this is pretty helpful. So the problem defines a score for every node. The score of a node it's kind of complicated, so let me draw this out. So let's have this tree over here. So like 0, 2, 4, 3, 1, right? 0, oh my goodness. 0, 2, 4, 3, 1. Basically, if we want to find the score of a node, we are asked to remove all the edges around that node. So for example, if we want to find the score of 2, we would erase all its edges, and then we're left with some, hang on. We also have to delete the node itself. So we're left with some subtrees, and they have to be non-empty, which is pretty trivial. But we count the sizes of these remaining subtrees, and then we multiply these together. So we do 1 times 1 times 2, which is 2, and that is the score of this node. So you can see there's a bunch of examples here, and the scores of the nodes are 3, 4, 2, 4, 4. Okay, so how do we actually do this problem? Well, you can see that the input is small enough, 10 to the 5, that we can just compute the score for every given node. So the question becomes, how do we compute the score for every given node? And how we do it is this. So let's say we have like a big binary tree here. Here's like a node n. It's connected to its parents, and it has some children. I first did some pre-processing to convert this into, rather than for every given child knowing its parents, into a structure where for every given parent, you know its children. So the way I did that was just looping through and kind of just like reversing the thing. So, you know, if you can make sense of that, that's good. That's actually the code up here. And then if you know prefix sums, I used a prefix sum-esque technique. So basically, for every node in the tree, I computed the size of its subtree. So if you look at this example again, the nodes are arranged in this structure. And okay, so we find the size of every node subtree. And okay, how this works is we take a node, we do some recursion, and the recursive function or method returns the size of its subtree, and then we just add on 1 for every iteration. So we'd start down here, DFS, we just, go deepest first. If a node has no children, then its size is 1, right? So these are all 1, although you wouldn't go in this order. Then for this one, when it calls the DFS on its children, it would add them up and then add 1. So it would be 1 plus 1 plus 1 is 3. Similarly, up here we get 4. Hey, Future William here. Sorry, that should be a 5, not a 4, because 3 plus 1 is 5. I forgot to add that extra 1. I will end up pointing out my mistake later in the video, though. So this is just the size of every node subtree next to that node. And then to compute whether a given node, what will happen when we remove all of a node's edges. Let's just draw an example here. And then we have some tree down here. Actually, it's binary, so it can only go like that. Node. Let's remove the node and its edges. So let's take all of these out. We're left with 3 things, 3 possible things. We are left with its parent, most definitely, and we are left with its children. How do we compute the size of the subtree of the parent? Well, that's pretty simple. We just take the size of the parent originally. So I'll draw in some ghosts here of a node. What would have happened if this node was still there was, in this example, we would have had 4, right? If 2 was our special node. And then what happens when we remove this node is that the 4 loses 3 of the nodes in its total size. The size of the subtree when this node is removed over here would be 4 minus 3 for the parent. And similarly for down here, actually not similarly, for the children, you just find the size of the subtree, because the subtree is just the subtree, because nothing is removed. So yeah, in this case, oh, actually, wait, 4 minus 3? No, this should be 5. What am I doing? We would do 5 minus 3 is 2. So like prefix sums, basically. And using that, we compute the size of every node. Actually, wait, yes? The score! The score, not the size. Yeah, that's what it's called. The score is the product of the size of the remaining subtrees when you remove a node. So that's what we do. Prefix sum stuff. You can look at my solution later. And yeah, that's pretty much it. We multiply stuff together. We get the score for every single node. And the problem actually asks for something specific, which is the number of nodes that have the highest score. So we just get the highest score and then return how many times it occurs. So yeah, this problem was a very interesting exploration of prefix sums as applied to binary trees. Okay, problem 4, parallel courses 3. So, kind of like, as this is probably a familiar structure, we have some amount of courses that are given in some directed acyclic graph. So let's take the second example over here. For every course, we are given the number of months it takes to complete. So this is 1 month, this is 2 months, this is 3 months, this is 4 months, and this is 5 months, which works out pretty nicely. What we are asked to do is we want to finish all of these courses in the least amount of time. But there are a few catches, which is that in these arrows, we have to take all the courses that have arrows leading up to it before we can take that course. So for example, before we can take course 5, we have to take courses 1, 2, 3, and 4. So there's some prerequisite stuff going on. And before we can take course 3, we have to take before we have to take course 4, we have to take course 3. We're given this structure in a list of pairs, which represent the prerequisite to course that requires that prerequisite pair. Yeah, another condition. These courses each take a set amount of time to take, right? But we can take several courses simultaneously. So we can take courses 1, 2, and 3 simultaneously. And then when we finish 1, and then we finish 2, and then we finish 3, we can then take course 4. And then after course 4 is done, we can take course 5. So what is the optimal way, basically? What is the fastest amount of time in which we can finish all of these courses? This is surprisingly similar to the last problem in some ways, where we're given like a tree structure, an implicit tree structure. What we do is we define a function again, which is the least amount of time it takes to complete a course and all its prerequisites. So in this example, course 1 would be finished in 1 month. Course 2 would be finished in 2 months, and 3 would be finished in 3 months. So that's pretty simple, right? But then course 4 requires course 3. So we would have to spend 3 months on course 3 and then add those 4 months on course 4, which gives 7. And this is basically what the recursive function is doing. Okay, and the course 5 requires all of these 4 courses. So which one are we going to finish last? Well, we're going to finish course 4 last. So it would take 7 months to finish all of the courses required, and we compute that by taking the max of all of the prerequisite courses. That's this over here. And this function is just calculating this is the recursive function that I talked about earlier, which I'm talking about right now, which is the minimum amount of time it takes to finish a course and all its prerequisites. So we take the max of all its prerequisites, which is 7, we add that to 5, and we get 12 as our answer. And at the end, what we actually have to do is, like, maybe there's a course 6 over here that requires, like, all of these, but which is independent of course 5, so 5 and 6 both have to be completed for us to be done. So to find those courses, we actually make a set which contains all the courses, and then remove all the courses that are prerequisites to end up with a set of courses that we have to finish eventually, which aren't prerequisites for anything. So we find those, which in this case with the added course would be courses 5 and 6. We find the total amount of time to finish all of them. So in this case, course 6 would take 3 months to finish, I believe, because we can do things in parallel. And then taking the max of that gives 12 courses still. So we take the max of all of those courses, and then we just return our answer. So This problem was pretty simple. There was one catch though, which is if you don't memoize, if you don't cache your results for the recursive function, you might get a time limit exceeded, which I think is what might happen. Okay, well, there's 8 minutes left in the contest. So I don't want to risk like getting like a penalty on this. But if you like, for example, course 6 and course 5 both require computing the minimum amount of time to finish course 3. And we don't want to like do redundant work. We only want to compute the function for course 3 once. So that's why we cache our past results so that we can refer back to them when we use them later. So that's problem 4. And indeed, that is the whole contest. So hopefully these explanations were helpful and easy to understand. As always, leave your feedback in the comments below. Hope you enjoyed watching. Thanks for watching, and I'll see you next time. Goodbye.